Problem 5. We wish to color each square in a 3 times 3 grid, either black or white. How many such colorings are there, such that the upper right and the lower left corners are colored differently? Oof, okay. So with this type of problem, I always like to visually get a sense of what they're really asking me. So I'm going to go ahead and make a figure to get started on this one. All right, so they're saying we wish to color each square. So we're talking about squares in a 3 times 3 grid, either black or white. Okay, what does that mean? Well, that means that we have a 3 times 3 grid. Let's make a quick one here. 1, 2, 3. 1, 2, 3. There we go. And they're saying that for each square, it can either be black or white. Let's just try to color one black. How many such colorings are there? So how many different type of grids can you have where they're colored differently, such that the upper right, which is this one right here, and the lower left, which is this one right here, corners are colored differently? Oof. Oh boy. Okay, so I suppose this one would be one of them, right? Because here you have black and here you have white and everything else is just white. That would be one of them. Let's try another one. So another one here would be, it's taking me a lot of time to draw these. So let's see. So let's say that this one was black, and then this one was black as well. And then this one was black. And yeah, that's another option, right? So this one is white and this one is black, which satisfies this criteria that they give us. This one right here. So that's going to be another one of those possibilities. But as you can already see, if you look at the options, it's starting from 81, is going all the way to 512. So do you think it's a good idea to find out all of those manually by coloring them in? Absolutely 100% not. No, that's going to keep us busy for a very long time. So how really to think about this then, right? Well, what if the grid was smaller? What if we were talking about a much smaller type of figure? Because 3 times 3 already has 9 different squares in it, and you can already see that there are so many options. So how about we make the problem simpler so that we can more easily understand what it is that they're asking us. So I'm going to do that. So I'm going to turn this into a 1 by 1 grid. And that obviously just has one square. All right, so let's forget about this one, upper right and lower left, because that's not something that you'll have when you only have one square, right? Let's just assume, like, what are the 2 different possibilities that you can have if they can either be colored black or white? Well, in the case of one square, it can either be black or it can be white. There's 2 options, 1, 2. Okay, 2 options. Well, what if we were to increase this by just 1 square? Let's now do 1 square and then another square. And let's say, again, we don't care about this criteria just yet. All we care about is to find out all the different options that you have if you can color them black or white. So let's think about that. So for the first one, that can obviously be either black or white, as we already figured out. And then based on that, the second one, if let's say that the first one was colored black, the second one could be either black or white. Okay, so either this one or it could be this one, both of them black, right? And then here, first one would be white, the second one would be black, and then in this case, first one would be white, and the second one would be black too. That's 1, 2, 3, 4. Okay, well, how are we really doing this? If we were to not write this out, or like rather draw it out, what are we doing? Well, we're just looking at each square individually, and we're saying how many options are there for each. And for each option, there's only 2 options because it's going to either be black or white. And so for the first square, it's 2 options. Second square is 2 options. So, and what we're doing to get this thing is we can just multiply those 2 numbers together, right? First, 2 options. The second one, 2 options. All right. That's going to give us these. Okay, now I'm starting to understand this a little bit more, because if we now were to look at a different grid, where it would be a 2 times 2 grid, now without even drawing all of the possibilities, I could solve this problem, this simpler problem. We're going to get to the harder one later. So let's go through each one. How many possibilities for this one? 2. Okay, we do that for the second one. Well, it's going to be 2 as well. 2 and 2. And so we get 2 times 2 times 2 times 2. That's 2 to the power 4, which is 16. Okay. Now we're getting somewhere. Let's get back to our original problem with a 3 times 3 grid. Okay, now again, I don't want to get to the problem as it is right now. We still have this criteria of the upper left and the lower left corners being differently. Let's take that away from now and just assume that the problem is asking us, in a 3 times 3 grid, each square can be either black or white. And how many different options are there if that was the case? Well, again, same thing. First one could be 2 for each one. And if we're going there one by one for each new square, you have to multiply each number to get all the possibilities for that. So for this one, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 to the power of 9. Okay, so that would be the, and whatever number that is, I'm not even going to bother calculating that, but whatever number that is. That would be, if this criteria wasn't added, that would be all the number of possibilities that you have to paint them black and white. But this is what makes it a little bit differently. So how can we think about this? Well, let's look at the criteria one by one. So let's go back on this. I can use the same figure. So it's saying, how many such colorings are there such that the upper right, this one right here, and the lower left corners are colored differently? All right, so they have to be colored differently. So let's look at the different possibilities we have just for that. So one option could obviously be that this one is colored white. Then, in order for this to be true, this one must be colored black, right? That's one. And then, of course, the rest of them can be colored whichever one. Now, the other option could be the opposite, which is the first one is colored black, and then the other one is colored just white. There are only 2 options. So what if we figured out for the first option, we color one of them black and the other one white, and then we figure out how many possibilities for the rest of it, and then we did the same thing for the second one, they added those 2 numbers together. That is actually going to work in this case. So let's do that now. So first thing we'll do is that we'll color the first one just white, this one, and then we must color this one black. So in this case, the coloring for these 2 squares have already been determined. We already fixed that. So what's what's up with the rest of them? Well, the rest of them are still going to be two possibilities, right? Because we don't have any restrictions on that. So this is 2, 2, 2, 2, 2, 2, 2. So for this category, we're going to have, let me take away this one. Let me have some more space. So the first one is going to be 2. So how many are these? There's 1, 2, 3, 4, 5, 6, and 7. Okay. So that's 2 to the power of 7. Now, of course, for the other one, it's going to be exactly the same, right? Because we're just flipping this and the rest are the same. So we have 2 to the power of 7 plus 2 to the power of 7. So now we just need to calculate this. So what we can do here is that we can figure out what 2 to the power of 7 is and just multiply it by 2, right? Because this is the same as 2 times 2 to the power of 7, like this, which actually, if you think about it, using exponent rules, is the same as 2 to the power of 1 times 2 to the power of 7, which really is just the same as 2 to the power of 8, right? And 2 to the power of 8 is 2 to the power of 4 times 2 to the power of 4. And what is 2 to the power of 4? Well, 2 to the power of 4 is 16. And this is, of course, the same thing. So now we have numbers here that we can multiply by each other. So maybe you already know how to do this in your mind or brain, but I'm actually going to write it out. So 6 times 6, that is how much? That's 36. And then we have 6 times 1, and then plus 3, which is 9. And then we have 1 times 6, that's 6. And then we have 1 times 1, that is 1. Let's add a little stair thingy here, and then we'll have 6. And 9 plus 6, that's 15. Up here, and we get, of course, a 256, which is the final answer. There you go. C is the right answer on this one. Now, before we're ending this video, just think about what we did here. This is a very good problem-solving technique, or strategy rather. If you find yourself thinking about this final problem is a little bit too difficult, try to make it into a simpler problem. And what we did was that we did it in a very structured way. First of all, we forgot about this criteria that made it a little bit difficult. And we turned a 3 times 3 grid into a 1 times 1 grid with just 1. But then we understood that a 3 times 3 grid is just a bunch of squares added together, right? And for each square, there's only 2 possibilities, black or white. And then we figured out, okay, so in order to get possibilities for a bigger grid or more squares, all you got to do is just multiply those possibilities together. In this case, it's easy, black and white, 2 times 2 times 2, however many squares there are. And then at the end, of course, we figured out that, well, there are only 2 possibilities for this case being true. Let's figure out the possibilities for one case. Second case together. Turns out they're the same number. Add them together, and there you go. So hopefully that was helpful. These problems can be a little bit tough, but if you do it in this way and you get a lot of practice with it, then they become easier, and more importantly, they even become a little bit fun.